This comes out of section 10.4, areas as limits. This is a kind of unusual example, definitely a departure from what we've been doing. If I were the author of your textbook, I probably would do this before we do all the integral area stuff that we've kind of been doing, the antiderivatives and things, because this kind of shows a little bit of where it comes from. What we have here is a graph of y equals x squared, and looks something like this. And we're being asked to approximate the area under that from 0 to 2 by dividing it into 4 intervals, so each little 0.5 units here, and using rectangles with right-hand endpoints. So what does that mean? It means at the right end of the interval I've got a rectangle like this, like this, like this, and something roughly like that. And so if I look at each of these, and my graph is quite small, so it's hard to label, but 0.5, 1.0, 1.5, and 2.0, I'll be able to just add up the areas. We know that the area of a rectangle is length times width. Each of these things has the same width. They're all 0.5 units wide. So I'm going to have, for the first little rectangle, I've got 0.5 units times f of 0.5, which ends up being 0.5 times 0.25, or 0.125. So that's the area of that first little rectangle there. Now if I do the same thing, I've got the width of 0.5, but the next rectangle goes a little higher. It's f of 1, which actually equals 1. So I've got 0.5 times 1 equals an area of 0.5. So there's your second rectangle. Now I go on to the third one. 0.5 times f of 1.5. That's where the height of that rectangle goes. So 0.5 times 2.25 equals 1.125. And finally, the last of the 4 rectangles, if I look at it, it's still 0.5 units wide, but it's now f of 2 units tall, which actually ends up being 0.5 times 2 squared, which is 4. And so it has an area of 2. So if I want to total up that area, I just add those 4 numbers together, and I'll get a total of, what is that, 3.75 square units. That would be a bit of an overestimation of the area. Hopefully you can see that even on my little diagram, because I'm not only just shading the area below the curve, I'm also shading little chunks of area that poke up above the curve. If I try left-handed endpoints, the opposite is actually true. If I draw my parabola again, and I go up to 2, but then divide that into 4 little sections. If I use left-hand endpoints, I'm looking at a little bit less than the actual area. In other words, when I do these rectangles, I'm going to have 0.5 width still, but the first one is going to be f of 0, which happens to be 0, so there's no area, there's no rectangle even to draw for a left-hand endpoint for that first little interval. The next one's 0.5 times f of 0.5, which, as we saw up above, was an area of 0.125. The next one, the width of 0.5, f of 1, is a left-hand endpoint, so 0.5 times f of 1 we know is 0.5. And finally, this last rectangle here has a width of 0.5, but a left-hand endpoint of 1.5. And when we did that, we got 1.125. If I add those together, I have 1.75, which is definitely an underestimation of what the area actually is. Because we've kind of skipped ahead and done this from 0 to 2 of x squared dx and said, oh, that's x cubed over 3, evaluate from 2 to 0, and we can find that the actual area here is 8 over 3, which is approximately 2.67 square units. So it is in between the overestimate and the underestimate, but this is kind of to show you a little bit introduction of where this is coming from. And so we'll do a tiny bit more of that in the next example.